what I'm going to talk about. You see my title here. I'm saying beyond the theory of everything paradigm. I'm talking there about current physics, which is trying to find a theory of everything, string theory and so on. I believe we're actually on the verge of a revolution in physics, based on the kind of ideas I'm going to be talking about here. And there are quite a number of people thinking in these ways, but it's definitely not mainstream. Most people won't have heard of it, or they'll discard it. But I think great progress is being made, and we know the path ahead, and I hope I'll be able to explain some of it. I have a paper that I've put on ResearchGate. If you go to ResearchGate and search on synergetic patterns and the natural world, or alternatively go to my homepage where I have a link to it, you will see a paper which gives some of these things in more detail. Anyway, let me move on. First of all, I must thank my colleagues. My main one is Mrityunjay Guha Majumdar. We're sort of he's written one version of a paper which is not that complete, but we're planning to get together and put our approaches together. He's a theoretical physicist and is doing quite a bit of a mathematical side. I've been concentrating on the biological side, and two other people, Scott Kelslow, Alexa Yardley, I've had quite a bit of discussions with. What I'm going to say is that the situation is quite like what it was in about 1900. Lord Kelvin talked about there being some clouds in the present theory. Did very nicely. There were just two little difficulties. You see from the slide, how can the Earth move through an elastic solid? And he talks about relative motion and ether and ponderable bodies. Now it's rather interesting because he'd picked on the two things which are part of the new physics, the ether and relative motion of ether. The problem there was solved by special relativity, and I think the Maxwell-Boltzmann distribution, I think that gave an infinite divergence, and that was solved by quantum theory. So he said, well, there are two little difficulties. In the same way, there are difficulties now, new clouds in physics. So I'll just list these quickly. There's Schrödinger's cat. Are there many worlds or just one? This still isn't very clear what should be happening there. Quantum entanglement. Well, that was quite surprising anyway. Einstein didn't quite believe it. And now there's evidence that quantum entanglement is a lot more prevalent than is all around the place, especially in biology. So in other words, there's a great unknown. Quantum entanglement. A thing which physicists don't think much about, but how does thinking work? It's no good saying it's just the brain, because we don't have explanations in terms of brain. That's not an explanation. And then there's paranormal phenomena, which are pretty controversial. Anyway, we need to build back better, which is a phrase our British government uses. Here, hope you can see this. There's a slide which was bent by a metal bender at a conference. This is pretty convincing because it's my key. He couldn't have brought his own key that he could fiddle with. It would require lots of force to bend it, and there's no movements. So it really seems that in some way his mind was making things change. Okay. No, I think the problem with physics is that it's got into a kind of routine. It likes nice equations that work nicely with Newtonian mechanics, with electromagnetism, and some versions of string theory. There's a nice equation, but nature is not that simple. In fact, we have a problem of complexity in the real world. So you might say physics isn't in the real world. It's not just that, because what some of us believe is that what biologists have found out about complex systems is actually the explanation of quantum mechanics, the quantum mechanical mysteries. Also, materialistic perspective, it looks at matter, particles, but there's more to reality than that. It also rejects the possibility of design. These rejections are not really scientific ones, it's a matter of ideology, I think. Okay, so now what I'm going to do next is go through my history, because actually back in the 1970s I got interested in this kind of thing. My postdoc year 65 to 66 I worked with critical phenomena with Kadanoff, but then my interest changed to brain function and the mind. Then Fritjof-Capra's book came out, Lindau Physics, which was saying that quantum physics seemed quite like mysticism. So I discussed this with my colleagues, late Michael Conrad and Dipankar Home. So we wrote a paper, not so much connections with mysticism and quantum physics, but quantum physics and biology. And here you see the key part of my paper. There are two, we have on the left things in quantum physics and similar things in biology. One particularly important thing is in quantum physics you have collapse of a state vector. In biology you have decision process. There's nothing mysterious about that. It's just ordinary processes. Nothing very mysterious, and you don't have many worlds. And there's what measuring instruments do. So if you go to my home page and follow the there's a link to my papers, you should be able to find these. Okay, after that I got interested in biological organisation, which is really the kind of thing I'm involved in now. A couple of papers, multi-stage acquisition of intelligent behaviour, with the person who started Acorn Computers and ARM, actually, he was at Cavendish. Development of that with a mathematician. And then I had a student who actually did a computer simulation. The lab was hostile to doing this kind of thing. Anyway, do I have here? No, I have. What's going on is that you have skills development stages. What this first paper showed was once you develop one skill, that skill can be used to develop another skill, and so it goes on systematically. And what Osborne was going to do was simulate this. Well, he did do 2 steps, hoped to go further, but he wasn't allowed to. So in other words, there's a kind of mathematics here of organisation, which hopefully will be of use when we apply these things to quantum theory. I'll also mention one thing I did was the connection between music and the mind. I had discussions with a musicologist and a letter on musical ideas. There was a musicologist I know who wrote an article saying there's no such thing as a musical idea. We said there is, if you think of it properly. Okay. Fairly recent paper. John Wheeler proposed that this collapse process could be used systematically to the laws of nature. Came about through the participation of observers in nature. That's quite close to what we're doing. He didn't have anything very detailed, but in biology, observation does things. So that's one way in which you might be able to proceed. Okay, well now, one point I made in one of my papers is that we've kind of got two cultures, physicists and biologists. Biologists and physicists each do things in ways that the others are not used to, so we need to bring the two together. And that will be the new direction in physics. Okay, I'm just going to list things. One of these studies by Scott Kelsler that I mentioned is coordination dynamics. That's about how systems work together in what's known as a synergy. And you can fit things to experiment using coordination dynamics. You find that these models fit experiment nicely. Then as science systems, that's information having meaning. Another similar study. So biologists are looking at messy details and they discover important regularities. So the question is, can these regularities be connected with physics, which is what I'm involved in. Well, one thing I think is very interesting, not many people know about this, but I was, for a couple of months, I was at MIT in the Artificial Intelligence Lab, and someone at MIT, Terry Winograd, did a very nice computer simulation of language. So, in a way, his program really showed what's going on in language. On the right is he had a simulated blocks world. You could ask it questions like, or feed in questions like, find a block which is bigger than the one you are holding and put it into the box. Pretty complicated sentence, and it's using the grammar that had been put into the program, it was able to understand these sentences. The way he did it was a kind of grammar which was based on called functional grammar, which is what it's saying, what is the functions of these various aspects of language. And he did this all in enormous detail, and program really worked. So this, I think, is giving a clue as to how biological systems work. And a conclusion is all these systems, they're like experts at particular things, and they all work in harmony. They do things which are consistent with each other. They survive because of expertise. It's quite like car driving. Car drivers discover how to work with other car drivers. A community develops ways of working together. So this is a very general phenomenon which appears to account for the complexities of language, at least I believe it would. It's also a bit like a system in equilibrium, and one of the things we're doing, and is in that paper, is that equilibrium in fact involves expert systems. I can't go into the argument here, but in order to remain in equilibrium, expertise is required, that's the thing. So we suppose that equilibrium states behave in some way like biology, and they may be creative. Now I'm going to go quickly through a number of ideas. One thing from coordination dynamics is that when one process doesn't work, you can switch instantly to another. And there's actually some mathematical model for that, the HKB model. And Winograd found that the same idea worked very well. Instead of having to search if one thing doesn't work, there's a secondary possibility available for you. So that is one. Let's see, what can I say about this? It's a concept which explains how systems function in in a skilled way, basically. Lots of these things are concepts which fit with how systems function. One aspect of a function is signs. Now, information is different in biology than in physics because it is meaningful, it does things, it's connected with a reference. And back in the 19th century, Peirce discussed this in great detail. It's not a simple thing at all. I think he found about 10 different ways in which signs work. That's to say, words, for example, act in a number of different ways. He discussed it in great detail. Then last century, biosimmeticians took up the idea in biology. One thing is code systems, which evolve special systems which give special meanings. In our picture, as my colleague's been developing, laws of nature come about because a law is stated in terms of symbols. Some actual physical activity is stating a law of nature and causing nature to behave according to that law. Rather nice idea. Haven't got it in full detail. Well, maybe it's in the paper, but it's hard to understand. So this will be a part of the physics that will replace present physics. So here we have collection of experts which are causing systems to bringing into existence laws of nature, just as human beings decide how some systems should behave. There's also the evolutionary perspective that, as I said before, one skill is the basis of another skill. And quote from a paper, the products of one kind of mechanism are handed on to another such mechanism for further constructions to be carried out. So what we envisage is that you have a system in equilibrium. A fluctuation causes a system which has got certain skills. Then they start combining with each other to get more elaborate skills, till eventually you are able to produce a universe obeying particular laws. That's the thing we'll be working on, and hope to have something coming out soon. Well, I won't say much about this, especially as I'm not supposed to be talking for much longer. But one phenomenon is bifurcation. One system splitting into two is part of coordination dynamics. Another collaborator, Yardley, says phases come into it as well. Phase variables, and phase variables are supposed to be a mechanism which causes these units, these synergies, to appear. So in other words, some instability causes phases to appear, and phases interact together to make more and more complicated things. There's also an argument for why you should get groups. I won't go into that. Well, I have a point here. If you can climb a given cliff, and then there was a cliff which was exactly the same but rotated, you would still, because of symmetry, be able to join the cliff. You wouldn't join the cliff, you just apply the symmetry operation. So that's roughly what symmetries do. So in other words, you could say symmetry is something which can be useful, and so that may be why we get it in nature. Okay, complementarity. Well, I won't say much about that, but it's just that certain things complement each other, the opposites. There's a book called The Complementary Nature. Crystallization is interesting because you could say a crystal's got a certain intelligence because you immerse a little crystal in a liquid and it grows, it knows how to grow. It grows it gets the atoms into just the right position for a crystal to grow. So it's a primitive form of intelligence, if you like, or an expertise. one of my colleagues, Shauna Dobson, has a theory she's working on which suggests that the origin of the universe is caused by the emergence of time, and said it was okay to say that in the lecture, something she's working on. So that's a fantastic idea. Before the universe, there's no such thing as time, and then some coordination process causes lots of times to go together, and that helps to produce the universe. So, right, I'm on my last slide now. These pictures were produced by PowerPoint. You can click on something and it makes all sorts of fancy things. This seemed to be a good thing to finish the illumination that this approach will give to physics, we hope. So, I'm talking about a radically new discipline. It will it takes a biological perspective, but it synthesizes all sorts of ideas. These all fit nicely together like a jigsaw. So we don't start with mathematics. We substitute insights deriving from the study of living systems, and what we're doing in particular is to consider the role of fluctuations, which I should have mentioned. An equilibrium state has got fluctuations. These fluctuations will organise myself, and we hope to have that in mathematical form. So is this the way ahead?